What's up, algebra bros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to talk a bit more about null space and column space, our favorite subspaces. We're going to get a chance to dive into this topic a little bit more, which is going to prepare us well for the rest of our course material. So some of this should seem like stuff we've talked about before, and that's good. We're reinforcing that then. So let's go ahead and talk a bit about it. Let's revisit the null space and the column space. The null space of an m by n matrix A, written as null A, is the set of all solutions to the homogeneous equation AX equals the 0 vector. And in set notation, null space of A is all x such that x is in vector space Rn and AX is equal to the 0 vector. Okay, we have a nice theorem here to coincide with this. The null space of an m by n matrix A is a subspace of Rn. Think subspace of Rn, n for null space, if that helps. Equivalently, the set of all solutions to a system AX equals the 0 vector of m homogeneous linear equations and n unknowns is a subspace of Rn. So we're talking about one of our favorite subspaces as the null space. This is a subspace of vector space Rn. We also have another favorite subspace, which is column space. The column space of an m by n matrix A, written as col A, is the set of all linear combinations of the columns of matrix A. If matrix A is a matrix where here the columns are written as the first column is little a sub 1, second column would be little a sub 2, so on and so forth. The last column would be little a sub n. Then the column space of A is going to be equivalent to the span of all of those column vectors, so the span of all of these vectors. If I take these columns out of the matrix, think of them as vectors, and then find the span of all of those vectors, that is the column space of A. And in set theory, we would say the column space of A is the set of all B such that B is equal to AX for some X in Rn. Now, with the column space, this is going to be a subspace of Rm. So the column space of an m by n matrix A is a subspace of Rm. So remember, null space is a subspace of Rn, n for null space. Column space is a subspace of Rm, m for M&Ms, the candy, or the artist. We also have the column space of an m by n matrix A is all of vector space Rm if and only if. So this is kind of a tall order. When is it going to be all of that vector space Rm? It's a subspace of it, but when is it going to be all of it entirely? That's if and only if the equation Ax equals b has a solution for each b in Rm. So we have to be able to achieve everything in Rm through the reach of our column space. And then we get to claim the entire vector space, which, hey, that's as good as it gets. Let's take a look at some examples. So we have a familiar one to start with, nothing too crazy off the bat. We have determined if this vector w, 1, negative 1, 1, is in the null space of A, where A is this matrix here as given. Now, to be fair, I could actually take this matrix and build a basis for the null space and try to investigate that way, but there's a much faster way to do this. If I'm given the matrix A and given a proposed element of the null space, which it might be, it might not be, there's a much faster way to check. Because we could say the following: if W is in the null space of A, then that means A times W has to be a solution to the homogeneous matrix equation. This must give me the 0 vector. Well, if I have everything here on the left-hand side, I have A, I have W, let's see if it gives me the 0 vector. So let's just do the multiplication. So let me take matrix A, I'm going to rewrite it. First row, 2, 6, 4. Second row, negative 3, 2, 5. Third row, negative 5, negative 4, 1. And I'm going to multiply that to this column vector W, 1, negative 1, 1. And I want to go through the multiplication and see what this gives me. Okay, so let's see here. What do I have? A 3 by 3 times a 3, so row by column. So 3 by 3 times a 3 by 1 is going to give me a 3 by 1 result. And I'm going to just make sure I have enough space. Let me not close it quite yet. Let's do our row vector rule. So if I fix this first row of A and then multiply into the vector, 2 times 1 gives me 2, plus 6 times -1, the second entries. 6 times -1 gives me -6, plus 4 times 1 gives me 4. And, whoop. Got a little carried away there. Let's take a look at that second entry, and we'll know what that's going to give us, but I'll do it later. Next, move to the second row of A. -3 times 1 gives me -3, plus 2 times -1 gives me -2, plus 5 times 1, the last entries give me 5. And then now this third entry, -5 times 1 gives me -5, plus second entries, -4 times -1 gives me +4. And then the last entries, 1 times 1 gives me 1. Let's go ahead and see what this gives us. Hopefully we got a good idea. 2 and 4 give me 6, -6 gives me 0. -3 and -2 give me -5, plus 5 gives me 0. 4 and 1 give me 5, -5 gives me 0. So I get the 0 vector out. So we can say, since A times W gives us the 0 vector, this means W is in the null space of A. So W, this vector W I was given, must be an element in the null space of A. Okay, well, what if it's not quite so easy? What if I'm not given a vector and asked that question? What if instead I want to find an explicit description of the null space by listing vectors that span the null space? And this is really going back to building a basis for the null space, and I can consider that to be a spanning set. So I'm given this matrix A, and really all that I want to do is I want to augment this with the 0 vector. So I'll rewrite it as a coefficient matrix. But then I'm going to augment with the 0 vector. And I want to solve this and build a basis. So say, well, what could I do to start? Well, first move I want to make is I want to scale row 2 by 1/3. So I'll rewrite row 1. And then dividing each entry of row 2 by 3, I get 0, 0, 1, 0, augmented with 0. And looking at my leading entries, thinking about pivot columns, that looks really good. Second row, well, I got to get rid of that 2 above my leading 1. So I should get rid of this 2, which means I want an operation in row 1. And to get rid of it, there's just that one operation that I'm considering, replacing row 1 with row 1 minus 2 times row 2. So 1 minus 2 times 0 gives me 1. -3 minus 2 times 0 gives me -3. 2 minus 2 times 1 gives me that 0 that I wanted. 0 minus 2 times 0 gives me 0, and then again in the augmented entry. And I can rewrite row 2. Now this is fully reduced, so I have my fully reduced version of this augmented system, and now I can start to build my solution. Well, what is this first row saying? The first row is saying x sub 1 minus 3x sub 2 equals 0. And the second row is saying x sub 3 equals 0. But it's also important to make mention of what my free variables are. So I have pivot columns 1 and 3, and my basic variables live in columns 1 and 3. So x sub 1 is a basic variable, x sub 3 is a basic variable, but it's those non-pivot columns that are going to give me my free variables. So column 2 and column 4 are going to be my free variables. So that means x sub 2 and x sub 4 are the free variables, which means I want to solve for x sub 1 and x sub 3 in terms of the free variables. Well, okay, so I can go ahead and do that. We could say x sub 1 is equal to 3x sub 2. And then x sub 2 is a free variable, so x sub 2 is equal to x sub 2. It's itself. I'm not really saying anything too expensive there. Now, x sub 3 is equal to 0. And then x sub 4 is my last variable, and this is equal to itself as a free variable. I'm going to leave some space because you probably know what I'm going to do. X sub 4 is equal to x sub 4. But this is good, right? And if we're comfortable with building a parametric vector form, then we can go ahead and just go right from here. But otherwise, we can actually introduce all mention of all free variables, which I think is useful. So x sub 1 is 3x sub 2, and then nothing else. So if I really want to include x sub 4, it has to be a 0x sub 4. X sub 2 is itself, so we'd say a 1x sub 2, and then plus 0x sub 4. X sub 3 is 0. Well, that's got to be a 0x sub 2 and a 0x sub 4, so that I don't disrupt that statement. And x sub 4 is itself, so that's a 1x sub 4, but if I want to include x sub 2, it's got to be a 0x sub 2. Now, the stuff that I've written in, it's not really changing what I'm saying, but it makes it easier to see how those vectors are going to decompose. Right, so we'd say, well, if I want to go ahead and build this, I can say that my solution on x, I'm going to have a vector that relies on x sub 2 plus another vector that relies on x sub 4. And the vector that relies on x sub 2, I can sort of look up the column here. Right, that's going to be 3x sub 2, and then 1x sub 2, and then 0x sub 2, and then 0x sub 2. And then the vector that relies on x sub 4, I can sort of look column-wise here. That's 0x sub 4, 0x sub 4, 0x sub 4, 1x sub 4. And I want to bring out the free variable as a scalar weight. I'll say, well, x is equal to, here if I bring out x sub 2, I'm left with just a numerical vector, 3, 1, 0, 0. Plus, here if I bring out x sub 4, I'm left just with a numerical vector, 0, 0, 0, 1. And it's these two numerical vectors, right? We're describing the span of these vectors, right? X sub 2 and x sub 4 are free weights, scalar weights. I can choose them to be any real number I want. This is going to generate a plane, a subspace, right? A two-dimensional subspace in R4, a plane in R4 dictated by these two numerical vectors. But I really want to view this as the span of these two vectors, right? I'm talking about the span of these two vectors. And I want to consider this to be a spanning set. So if I want an explicit description of my null space, say that the null space of A has the spanning set given by these two special vectors. So these two vectors. Put them in a set, curly braces, separate by a comma. It's the vectors 3, 1, 0, 0, and then the vector 0, 0, 0, 1. It's really building this spanning set, like building a basis, right? We'll take a look at one more example. I'm given a matrix A. Remember what I want to do is I want to start by just augmenting this with the 0 vector. Let's go ahead and see what's going on here. Let's take a look at those leading entries, those pivot positions. So here's my leading entry. Its column looks perfect. And here in my second row, I have a leading entry. I got to fix that column. Don't let me forget. And then nothing in this third row. I just pass right through a whole bunch of zeros. So really, I'm looking here at this second column. I have my pivot position right here in the middle. I need to get rid of this 3 up above. So that's what I'm going to focus on with my row replacement. I want to replace row 1 with row 1 minus 3 times row 2. So we get 1 minus 3 times 0 gives us 1. 3 minus 3 times 1 gives me that 0 that I wanted. Negative 4 minus 3 times negative 3. Careful with the double minus signs. That's negative 4 plus 9 is going to give me 5. Negative 3 minus 3 times 1. That's negative 3 minus 3 gives me negative 6. And then 1 minus 3 times 0 gives me 1. And then augmented with 0 minus 3 times 0 keeps my 0. And I can rewrite rows 2 and 3. Now this is fully reduced. Right here I just have the two pivot columns, column 1 and column 2. So x1 and x2 are my basic variables. But then x3, x4, and x5 coming from column 3, 4, and 5 are my free variables. And that's worth making a note of, right? So as I'm saying it, I should maybe jot down an idea. So that means column 3, 4, and 5 are not pivot columns. Those are where my free variables are, which means x sub 3, x sub 4, and x sub 5 are the free variables. Well, let's go ahead and see what these equations say. Let's solve for the basic variables x1 and x2. The first row is saying x sub 1 plus 5x sub 3 minus 6x sub 4 plus 1x sub 5 is equal to 0. And the second row is saying x sub 2 minus 3x sub 3 plus x sub 4 is equal to 0. And this last row is just saying 0 equals 0, which, is true, but it's not very helpful. Now let's see if we can solve the basic variables in terms of the free variables. So if I solve for x sub 1 in this first equation, we'll say, well, x sub 1 is equal to a negative 5x sub 3 plus 6x sub 4, and then minus x sub 5. And if I solve for x sub 2 in this next equation, x sub 2, remember I got to move these terms over, so here I got to add it over, I got to subtract it over. So x sub 2 is equal to positive 3x sub 3 minus x sub 4, and then I'm really missing that x sub 5 term. If I really want to see it, I could say, well, let me do this in a different color so it stands out. You could say, plus or minus doesn't matter because it's going to be a 0 x sub 5. And then remembering that x sub 3, x sub 4, and x sub 5 are the free variables, we can start to build this parametric description. So x is equal to, I'm going to get a vector that relies on x sub 3 plus a vector that relies on x sub 4 plus a vector that relies on x sub 5. And the very first entry is x sub 1, right across the top. And x sub 1 is a negative 5x sub 3 plus a 6x sub 4, and then a negative 1x sub 5. I like to write the 1 in just so I can help build that numerical vector a bit easier. X sub 2 is the second entry. That is a 3x sub 3, a minus 1x sub 4, and then no mention of x sub 5, so that's got to be a 0x sub 5. Now the rest, the other three entries, are for x3, x4, and x5, and those are my free variables. So x3 is itself, so that's 1x3, but no identity crisis, it's not 0x4, it's not x4, it's not x5, so 0x4, 0x5. The next entry is for x sub 4, that's 1x sub 4, but it's no x sub 3 and no x sub 5. And the last entry is for x sub 5, the free variable. So that's 1x sub 5, we got no x sub 4, we got no x sub 3. So we're starting to build these vectors. You know what happens next. I want to bring out my free variables as scalar weights. So x sub 3 times a numerical vector plus x sub 4 times a numerical vector plus x sub 5 times a numerical vector. When I bring out x sub 3, what am I left with? Well, I can see the values. If I've written it this way, that's the vector negative 5, 3, 1, 0, 0. This next vector, if I bring out x sub 4, what am I left with? That's 6, negative 1, 0, 1, 0. If I bring out x sub 5, what am I left with? That's negative 1, 0, 0, 0, 1. It looks like I'm almost running out of space, but I can write out my spanning set now. So we'll say null space of A has spanning set. It's going to be these numerical vectors here. So I want to build my set, 3 vectors. So I'll start with 3 empty boxes. Separate with the commas. First vector, that's negative 5, 3, 1, 0, 0. Second vector is 6, negative 1, 0, 1, 0. Third vector, negative 1, 0, 0, 0, 1. So here I have my spanning set, and this is going to describe the span of these vectors describes my null space for this matrix. All right, let's go ahead and talk about some things sort of similar to what we talked about in the last section, still sort of building off of those ideas. For the given set, capital W, use an appropriate theorem to show that the set W is a vector space, or find a specific example to show that it is not. And remember, we have a really nice shortcut to this. If I want to show organically that something is a vector space, I have to show that it satisfies not one, not 2, not 3, but 10 vector space axioms. That's a lot of work, and I don't want to do that. So what is our workaround? Our workaround is as follows. Say if we can show that W is a subspace of a known vector space, then it is its own vector space. And this is kind of a tricky thing to sort of think about or to discuss, but really the idea is if I can show that I have a subspace of a known vector space, then I can refer to it as a vector subspace, and in its own right, it is think of it sort of like a smaller, though it can be the entire space itself, so not necessarily, but try to think of it like a smaller vector space. For example, you could make an argument that if you have some two-dimensional subspace of R3, that could be serving as R2, which is also a vector space, right? So that's sort of reasonable to think. So sort of give that sort of give that some thought, right? You say, well, what if I have vectors 1, 0, 0 and 0, 1, 0 in R3 in 3 dimensions? That's going to be a two-dimensional subspace of R3, so it's a subspace of R3. But when thinking about it visually, even though the vectors live in R3, the vectors don't live in R2, if you think about it geometrically, the interpretation is that we're really getting the entire Cartesian plane then, and we're sort of getting vector space R2 from that two-dimensional subspace of R3. So that subspace is a vector space in its own right. And really what we're thinking of is we're thinking of those 10 vector space axioms. We're thinking about numbers 1, 4, and 6 as being some of the stronger ones, perhaps, and that the rest of those properties that we have almost follow suit, so to speak. Anyways, hey, that's enough about my day. Let's talk about this example. So here we're talking about vectors in R3. How do I know? I have a vector with entries RST, so 3 entries, such that 3r minus 2 is equal to 3s plus t, where r, s, and t are real numbers. So far, everything looks pretty normal. But if I want to argue that this is a vector space, then I want to show that it is a subspace of R3. And to show that something is a subspace means I have to check 3 properties. I need to have the 0 element, or the 0 vector. I need to be closed under addition. So if I take 2 elements in that alleged subspace, or call it a subset for now, if I take 2 elements in that subset and add them together, I have to stay in that subset in order for it to be a subspace. And I have to be closed under scalar multiplication, meaning if I take an element in that subset and multiply it by any real number, anything, no matter what it is, I have to stay in that subset. If I can pass those 3 conditions, then I have a subspace. Okay, so that's good. So we can just start with that first one that we mentioned, and maybe you're already sort of, grinding your teeth a bit. 0 vector. Do we have the 0 vector? How would the 0 vector look in this case? The 0 vector in R3, there's not a lot of opportunities for it. It has to be 0, 0, 0. What does this mean? This means that R must be 0. This means that S must be 0. This means that T must be 0. However, there is only one rule that these vectors have to follow. That is that 3 times r minus 2 must be equal to 3s plus t. Uh-oh, right? If this is what I have to obey, let's see what happens. 3 times r, but r has to be 0 for the 0 vector, minus 2 has to be equal to 3 times s, but s has to be 0, plus t, t has to be 0. What is this gonna tell me? I don't like it already. So I get 0 minus 2 is negative 2, equals 0 plus 0 is 0. How does this make you feel? I don't feel good. It makes me feel a little sick to my stomach, because this is not true. It's not true. So this is no good. So the only rule that we had for the vector, not going to work, right? I have to disobey it in order to get to the 0 vector, but I'm not allowed to. This is the one thing that I have to abide by. I can have any real number provided this relationship is true. 0 vector, That's bad news, right? I can't have the 0 vector then, because it's going to break this only rule that I have to follow. Well, besides the fact that I got to pick real numbers, and then I got 3 entries. So since we fail right away, we wouldn't really necessarily feel the need to go on and check those other 2 properties. You certainly could. It's not a bad idea, but right away we have the answer, right? Since this is not a subspace, so W is not a subspace of R3. Since it is not a subspace, we can say this is not a vector space. And then depending on how that makes you feel, I know how it makes me feel, sad face. It's very unsettling. It's very upsetting. Okay, back in it to win it. Let's take a look at another example. For the given set capital H, use an appropriate theorem to show that H is a vector space, or find a specific example to show that it's not. Same idea, right? If I can show that this is a subspace of a known vector space, then it too will be a vector space. And that's better because I don't have to check 10 things on a list. I can just check 3 things. What do I have? It looks like I have vector with entries A, B, C, D, such that 3A plus B is equal to C, and A plus B plus 2C has to be equal to 2D. That's what I have to be abiding by. Additionally, that A, B, C, and D are real numbers. I'm not working with complex numbers, real numbers. Okay, well, so this is sort of interesting. The way that this problem is laid out, there's actually a couple ways that come to mind. And I'm going to show you both ways that you can go about doing this. Let me know in the comment section below which one of these 2 ways you think makes more sense, that you would have thought to do, that you prefer. Let me know what you're thinking and feeling. But let me go ahead and take a look at what we can do here. Now, when I want to show that this is a subspace of a vector space, well, I can pick on my favorite subspaces. That would be null space and column space. So I could talk about spanning sets with column space. I could talk about spanning sets with the null space. I could try to build an example of that. Let's do null space first, and then let's do some argument more about a spanning set second. I'm going to do both of these. Since I have these equations given, the equations that I'm given really lend itself to talking about null space. And if I want to think of this as a homogeneous equation, I would just go to these 2 equations and set them equal to 0. So 3a plus b, and then subtract c, so minus c, equals 0. And then a plus b plus 2c, and then minus 2d equals 0. And I can actually use this description to construct a matrix. So if you want to think about it this way, you could say, well, this could be some matrix A times a vector of this form, A, B, C, D, equals the 0 vector, right? Equals the 0 vector. And what I can do is I can construct from this a matrix, so equals the 0 vector. And we'll say, well, let's go ahead and sort of figure this out then. So what I'm going to wind up with is I'm just going to be picking on coefficients. So it's going to be the 3 times A, so write the 3, plus 1 times B, so write the 1, minus 1 times C, so write the minus 1. And then I'm missing D here, so that's really 0D, so I have to write the 0 in. And then for the second row, it's the second equation. So that's 1A, write the 1, 1B, write the 1, 2C, write the 2, minus 2D, so write the minus 2. And if I go ahead and multiply this back together, we're just going to get these equations, right? 3A plus B minus C plus 0D equals, there'd be a 0 entry there for that. Second equation, we get 1A plus 1B plus 2C minus 2D. We can sort of think about sizes here as well. So what about this matrix? We have a 2 by 4 times, here we have a 4 by 1. So the product is defined and the result is a 2 by 1. So this vector that I get out is really going to be the 0 vector in R2. We say, well, this is actually going to work then. So 0 vector will really mean the 0 vector in R2 since we have those 2 equations. So everything's working really well here. Okay, so then what can I say? Well, I can make a very quick argument. And the quick argument I can make is I can say that And this set was called what? H. I can say that set H describes the null space of A with A equal to this matrix. I can just write the matrix. What was that? 3, 1, negative 1, 0, 1, 1, 2, negative 2. And I know that there's going to be some element in this null space, right, no matter what, and it's going to give me some subspace. So I am going to get some subspace then. So this is one possibility, right? And this, I think, is maybe the quicker way of doing it. But there's another way that I could even do this as well. Let's go back. Well, let me use this other piece here and show you another way we could do this. We could say H is a set of vectors A, B, C, D, such that, and what were my equations? You're going to like this one too. 3A plus B equals C. And we had one more. A plus B plus 2C equals 2D. And we remember A, B, C, and D have to be real numbers. So A, B, C, D have to be elements in our real number system. This is what we were given for our restrictions. Now what's nice about this is I can use these equations, if I'm not trying to treat them as homogeneous equations, to build some argument around a null space for my subspace. I can use these equations as substitutions, right? So right away, I actually have a substitution for C, that C is the same as 3A plus B. I can go to this other equation though, so let me actually write that down. So we'll say C is equal to 3A plus B. They gave me that one. But then with the other equation, we have A plus B plus 2 times C equals 2D. And here 2 times C, but C I can replace with 3A plus B, and that's equal to 2D. Let me work with this other equation a bit. So that's A plus B plus distributing. I get 6A plus 2B, or not. That is the question. A little Shakespeare joke for you. Let me know if you like Shakespeare in the comment section below. Equals 2D. Let's collect like terms. So A plus 6A gives me 7A. B plus 2B gives me 3B equals 2D. And I can solve for D. So we could say, well, okay, that means D is equal to 7 halves A plus 3 halves B, just dividing by 2. So I actually have 2 substitutions, which means that when I go to describe my vectors are of the form A, B, C, and D, and I use those 2 equations to now use substitutions. I'm going to leave A as A, I'm going to leave B as B, but then C, I can replace C with 3A plus B, and you could do other substitutions. The idea is the way that I'm given the information, I should be able to eliminate 2 of the parameters and just end up with the remaining 2 to work with. And then D is 7 halves A plus 3 halves B. And now from this, you probably know where I'm going with this. If you can't tell, let me actually do this. I think you're going to like this a lot. Let me know in the comment section below if you like this a lot. I'm going to do, so B is B, but I'm going to write it over here. So you can kind of see what I'm going for, because I can now split this into 2 vectors. Right, 1 vector relying on A plus 1 vector relying on B. I'm going to have A and then 0A, and then 3A, and then 7 halves A. Think of A like 1A. And then for the next vector, on B, we have no B, so 0B, 1B, 1B, and then 3 halves B. And I can bring out A and B as scalar weights. So A times numerical vector 1, 0, 3, and then 7 halves, plus B times numerical vector 0, 1, 1, 3 halves. So I can describe this with a spanning set. Right? I could say set H has a spanning set with these 2 vectors, 1, 0, 3, 7 halves, and 0, 1, 1, 3 halves. We kind of get some options for this one. You want to describe it with a null space? I did too. I did that. Very lazily too. Or we can build a spanning set. It all depends on how you sort of receive this information. Do you notice right away we have equations that we can set to 0? Do you try to think of it as a homogeneous equation, some homogeneous system? Or do you start making substitutions to try to build a spanning set? Both are fine. Let's take a look at one more example. And I think we should be ready to move on in our journey. This is sort of reinforcing what we talked about a bit before and seeing some really cool examples. I want to find a matrix A such that the given set W is the column space of A. And here I have a vector with entries B minus C, 2B plus 3D, B plus 3C minus 3D, and then C plus D, where B, C, and D are all real numbers. And notice no mention of A. Don't worry about it. Does it look a little funny? Maybe. Do I need to do an order of the alphabet? No. So just kind of get over it, I guess. We have vectors in R4, and then we have this description of them, and that B, C, and D have to be real numbers. Now, what I would like to do to describe this as the column space of a matrix is to try to think about how that matrix A would look, right? So we're sort of trying to think about AX equals B. I'm trying to think about where the columns of A can take me, but I really just want to try to find this matrix A. So what I could do to start is I could actually write out this vector, and it looks great as it is, but some of the terms are missing. So I'm going to write in all coefficients very visibly and every mention of B, C, and D, even if it's missing, which some of them are, but not always. So the first one is almost there. That's 1B minus 1C and then plus 0D. Second one is missing C, so that's 2B plus 0C plus 3D, because C is missing. This third entry is actually fine. I'm just going to write in the missing coefficient so I can see it a bit better. 1B plus 3C minus 3D. And this last entry is missing B, so let's do 0B plus 1C plus 1D. But ultimately it's the same. I've just written it out a bit more detailed. But what I can do from this is I can now think about sort of building this into matrix multiplication. I want a matrix A times some vector with entries B, C, and D. Well, and I can do this now. So I'll say, well, okay, so I'm actually kind of staring, if I ignore the B, C, and the D and the operations, I'm kind of staring at what that coefficient matrix should be. It's 1B minus 1C, 0D, so I write the coefficients. For the next row, it should be 2B, 0C, 3D. For the next row, should be 1B, 3C, minus 3D. And for the last row, should be 0B, 1C, 1D. So this is what we're sort of looking at or thinking about when we write this. Let's just check, make sure that the sizes make sense for this product. What do I have here? How many rows? 1, 2, 3, 4. So I have a 4 by 3 columns. And I'm multiplying this to 3 by 1 vector. So the product is going to be defined, and the result is going to give me some 4 by 1 vector, a vector in R4. But this is the description that I would like, right? This is the description that I'm looking for, right? So it was asking me to build a matrix A such that this given set with all of its detail is the column space of that matrix A. Well, it is the column space of this matrix that I've just built. So we can say W is the column space of A with matrix A, where matrix A is this matrix here. So I am going to rewrite it. 1, negative 1, 0 for the first row. Well, we got 2, 0, 3. We got 1, 3, negative 3. And 0, 1, 1. So that's what we got. We got column space of A with this is our matrix A to describe it, just as we were asked to do. Hey, if you made it this far, thank you so much for hanging out with me. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, to always follow your heart. You know what? I'm going to see you soon. We're going to be doing more stuff with math and cats. But until then, take care, and don't forget, I will see you next time.